Alright, this is example 2 in Module 12. We basically have a pretty straightforward two-lens system. We're told that we have two convex lenses that are separated by 10 centimeters, and we're given the focal lengths of each lens. And then we place an object 6 centimeters in front of the first lens, and the first lens is the one that is in front. So with these two lens systems, what we need to do is we basically treat each lens completely separate. So the first lens, which is the one that's in the front, so the lens closest to the object, we can basically do without considering the second lens at all. And what we're going to do is we're going to find the image that is formed by this front lens. And then when we find that image, we're going to take that image and treat it as an object for the back lens, and we're going to completely ignore this front lens. And that's the procedure that we'll use for any multiple lens or mirror system. You just treat each one of them separately. You start from the front and you work your way through to the back. So for this first part, we're going to use the image equation, right? So we know that 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. Now we have a sign convention. So these quantities can all be positive or negative, and we need to make sure that we get that sign correct when we do these calculations. So the arrow I have drawn here, 6 centimeters in front of the front lens, that's our object. We could do a ray diagram to sort of estimate where this image is going to be formed. So to do the ray diagram here, I would draw a parallel ray coming off the top of the arrow. And any ray that comes into that lens parallel to the optical axis is going to be bent towards the focal point of that lens. And the focal point for that front lens is actually all the way back here. That's F1. So let me use a different color for this. So I have a ray that comes in here, and then it's going to be bent towards that focal point. And then any ray that comes through the center of the lens isn't bent at all, so I can draw a ray that goes through the center here, and that's not going to be bent. And we can see that these are not going to converge to a single point, which means that the ray that is bent towards the focus, we need to project back towards the object. And we need to find the point where these rays come together. So, this isn't drawn to scale, but you can get the idea that these rays projected back are going to give me an arrow right here. So we can see that this image is going to be formed farther away from the front lens than the object is, and that image is going to be bigger than the object. All right, so let's do the actual calculations. So I've got the object distance, which is known. So the object distance here is, since the object is in front of the lens, that's going to be a plus 6 centimeters. I know that the focal length of this lens this is a convex lens, which means it has a positive focal length, so it's going to be plus 24 centimeters. Now the image distance can be calculated then, because I have 1 over the image distance is going to be 1 over the focal length minus 1 over the object distance, which means that the image distance is going to be the inverse of 1 over f minus 1 over do. So I take the numbers that I have, I plug those in, and for the first lens, so let me write this as lens 1, oh, not lens T, lens 1. For the first lens, I get an image distance that is equal to negative 8.0 centimeters. Now, how do I interpret this negative sign? Well, for image distances, the image distance is positive if the image is on the side of the lens that light is going to. So that would mean over here, on the right side of that lens would be positive image distances. And on the left side of the lens is negative image distances. So it's really where the light is going to that defines the positive distance. And I mention that because for a mirror, in terms of front and back, it gets switched, but it's always consistent when we think about what direction is the light going. So if we have an image that's formed on the side that light is going to, then we get a positive image distance. Now we know that that image distance should be negative because we just drew a ray diagram, and it shows that the image is on the same side of the lens as the object. All right, so -8 centimeters is the image that's formed by the first lens. Now what we need to do is we need to figure out this image can be treated as an object for this lens. Where is the image formed by that lens going to be? And we could draw another ray diagram here if we wanted to. And we see that the image, well, let me refer to this as the object now. We see that the object is outside of the focal length, so we expect the image formed by lens 2 to be behind that lens. So let's just do the calculations. So for lens 2, I still have 1 over DO plus 1 over DI is equal to 1 over F. And now what I have to do is figure out what these quantities are for the second lens. The focal length is given, so let's just write that down. It's a convex lens, so this is going to be plus, let's see here, this is plus 9 centimeters. The object distance, we need to figure out how far away the object that this lens is creating an image of is from the lens. And so to do that, we need to go up here and look at our diagram. Now we know that these two lenses are 10 centimeters apart, right? That's written at the top, that's 10 centimeters. We also know that this image formed by the first lens, so clearly this isn't drawn to scale, but we know that that is 8 centimeters. So that means that this red arrow that I have drawn here is 18 centimeters in front of the second lens, and that's what we need to use for our object distance. So this is 18 centimeters, and it's in front of the lens. That's going to be plus 18 centimeters. So the image distance then can be calculated, and that is going to be 18 centimeters plus as well. And this is just an example of, you know, the focal length of this lens is 9 centimeters. If you place an object that is twice the focal length away, then you get an image that's formed twice the focal length away as well. But again, we need to interpret this plus sign. So this plus sign means that the image distance is positive, which means that the image is going to be formed behind the second lens. So let me go up here and draw the ray diagram for the second lens. So we now have this object here, ray that comes in parallel to the lens. It doesn't matter that this ray doesn't reach the lens. This is just an example ray, right? You could just draw your lens bigger if you wanted to. So a ray that comes in parallel to that lens is going to be bent towards the focal point of that lens. So it's going to go through F2 like this. And then a ray that goes through the center of the lens won't bend at all. And where those two meet then is the position of the image that is formed. So I'm going to have an image that is upside down behind that second lens. So there we are. We have the position of the final image that's formed by the two. So there's a couple of ways I could write the position of that final image. I'm going to say that the final image is 18 centimeters behind the second lens, or I could write that it is 28 centimeters behind the first lens, right? Because those two lenses are 10 centimeters apart. The second question asks whether or not this is a real image. Now, fundamentally, what makes an image real is whether or not you can project that image onto a screen. So can I put a sheet of paper where the image is formed and get that image on the sheet of paper? And in order for that to happen, you basically just need to have an image that's formed behind your optics. So if I put a sheet of paper here, the image that's formed can be formed on that sheet of paper. The first image that's formed, so if I just completely ignore the second image, right, I could not put a sheet of paper here and get an image formed on that sheet of paper, because the light rays, this is an image that's formed behind the object. The light rays are going to the right. So no light rays actually go back to that sheet of paper. That's just where a placeholder for where that image would be, and I could create a real image of that with a second lens like I've done here. So basically, I guess another way that you could think of it is, if the actual light rays physically go through the image that you have drawn, then it's going to be a real image. The light rays physically go through this image here, so it's going to be real. They do not go through this image here, so that's going to be virtual. And so there's an important point. A virtual image is an image that can still be used as an object for a second lens to create a real image. And that's exactly what we've done here. So we have a real image that's formed at the end. The last part asks us to calculate what the magnification is. So the magnification for a multiple component system is just the product of the magnification for all of the lenses in the system. So for example, if we have a lens that's going to magnify an image, it's going to double the size of an image over an object, and then we have a second lens that's going to triple the size of the image over an object. Well, the first lens is going to double the size. The second lens is going to triple that, which means that it's going to actually end up with a 6 times magnification. So we just need to calculate the magnification for each lens, and then we're going to multiply those together. The magnification is the ratio of the image height over the object height, but we can also write that in terms of the distances. So it's negative image distance over object distance. So that is going to give me a negative 8 centimeters over the object distance, which was a plus 6 centimeters. So I could write centimeters here, which is going to give me a 4/3. That plus sign on the magnification means that the image is not inverted. And that's exactly what we saw, right? This image is not inverted, and it's also bigger than the object. So we see that the magnification is plus 4/3, which means the image is larger than the object, and it is not inverted. We need to calculate the magnification for the second lens now. So the magnification is going to be negative di over do. And that is going to be negative 18 centimeters over the object distance here was 18 centimeters. So that gives us a -1. That means that the image is the same size as the object, but it's inverted. The negative sign means that it's inverted. So the total magnification is just the product of these. So I have 4/3 and a -1, -4/3. That means that the final image is inverted and it's larger than the object. So there we go. That's an example of a 2-lens system. If we have 2 lenses or 3 lenses, or if we have a lens and a mirror, what we need to do is we start out with the object, we analyze the first component that the light rays are going to go through, so in this case it's this front lens. We figure out where the image is, then we ignore that first component, take the image that's formed and treat it as the object for the second component. In that case it was this one right here.